Conditional statements. Part 1 Basics. Exercise 1. 1. The problem review. Let's begin with our first problem. Exercise 1. Write a program that inputs two integers, a and b. Find the largest value. This is a classic comparison problem. The computer needs to make a clear two-way decision. Is a larger than b, or is b larger than a? This immediately tells us we must use the fundamental if-else structure from Lesson 3.01. 2. Required setup. Input. First, we need to handle the input. We need two integer variables, a and b, and we need to use scanf to get the values from the user. 3. The core logic if-else. We are looking for the largest value. The most straightforward way to solve this is to ask, is a greater than or equal to b? We use the comparison operator, greater than or equal to. Using the or equal to part is critical because if the user enters the same number for both, like a equals 2 and b equals 2, the condition is greater than or equal to b is true, and the program correctly outputs the number 2. 4. Review and final solution. Let's trace the logic with the examples. Example 1. Input A is 3, b is 7. The condition is checked. If 3 is greater than or equal to 7. This is false. The program skips the if block and runs the else block. Output. The largest value is 7. Correct. Example 2. Input A is 2, b is 2. The condition is checked. If 2 is greater than or equal to 2. This is true. The program runs the if block. Output. The largest value is 2. Correct. This solution uses only the core concepts: variable declaration, scanf, for input, the if-else control structure, and the is greater than or equal to operator. Simple, clean, and efficient. 1. The problem review. Next up is exercise 2. Write a program that inputs three integers, a, b, and c. Find the smallest value. This is a step up from the previous problem because we now have three variables to compare, meaning more possibilities. We are looking for the minimum value. Just like before, we start with the setup. 2. Required setup. Input. We need three integer variables, a, b, and c. 3. The core logic, the chained if-else approach. To find the smallest value, we can simply check each variable against the other two. We ask three sequential questions, forming a single chain that guarantees only one path is executed. Is A the smallest? If not A, is B the smallest? Else if not A and not B, then C must be the smallest. Else. This is the most logical and efficient way to solve it with our current toolset. 4. Review and key takeaway. Let's trace the logic with one of the examples. Example. Input A is 4, B is 5, C is 2. The condition if A is less than or equal to B and A is less than or equal to C is checked. 4 is less than or equal to 5 and 4 is less than or equal to 2. This evaluates to true and false, which is false. The program skips to the else if block. The condition else if B is less than or equal to C is checked. 5 is less than or equal to 2. This is false. The program skips to the final else block. Output. The smallest value is 2. Correct. The key takeaway here is the power of the logical and operator. By combining A is less than or equal to B and A is less than or equal to C, we can check multiple conditions simultaneously to isolate the true minimum in a single, elegant control flow structure. 1. The problem review. Our third exercise is a practical application of C programming. Write a program that inputs student scores, attendance 10%, midterm 30%, final exam 60%. Calculate the average score and classify it according to the defined rules. This problem requires two stages. First, arithmetic for the weighted average, and second, control structures to determine the final grade. 2. Setup and the data type rule. Because we are dealing with percentages, the final average score will certainly be a decimal number. Therefore, we must use the float data type for all our scores and the final average score. 3. The classification logic order is critical. We have 4 possible outcomes: grades A, B, C, D. So the if-else chain is perfect. Remember the rule from lesson 3.02. Always check the most restrictive condition first. Grade A, score 9 and above, is the most restrictive, so we start there. 4. Review and final code. Let's trace one of the tricky examples. Attendance is 8, midterm is 7, final exam is 9. The calculation is 8 times 0.1 plus 7 times 0.3 plus 9 times 0.6 equals 0.8 plus 2.1 plus 5.4 equals 8.3. Average score is 8.3. If 8.3 is greater than or equal to 9, false. Else if 8.3 is greater than or equal to 7, true. The program stops here and outputs final grade, grade B, correct. The structure works perfectly because the if-else chain ensures that only the highest matching grade is ever selected, giving us a clean and correct solution. Exercise 4.1. The problem review. Our final challenge in this section is exercise 4. Write a program to solve a linear equation of the form ax plus b equals 0. This problem is primarily about conditional logic, not just calculation. The program must analyze the coefficients a and b before it attempts to calculate the solution. This is a perfect case for the if-else structure. 2. Setup and data types. Since the result of division, the solution for x, will almost certainly be a decimal number, we must use the float data type for the coefficients a and b, and the solution x. 3. The core logic if-else chain. We must check the edge cases first. The most problematic cases are when a equals 0. Case A. Infinitely many solutions. A equals 0 and b equals 0. If both a and b are 0, the equation becomes 0x plus 0 equals 0. Any value of x satisfies this, so we have infinite solutions. We check this first because it is the most restrictive and complex exception. Case B. No solution. A equals 0 and b is not 0. If a is 0 but b is any other number like 2, the equation is 0x plus 2 equals 0, or 2 equals 0. This is a contradiction, meaning there is no value of x that can solve it. We use else if to check this case next. Case C. Unique solution. A is not 0. If neither of the 0 cases for a were true, a must be a non-zero number. This guarantees a single, unique solution. We use the final else block for this, and solve for x equals minus b over a. 4. Review and final code. Let's trace the logic with the examples. Example 1. A is 1, b is 2. If 1 is equal to 0 and 2 is equal to 0? False. Else if 1 is equal to 0. False. Runs the else block x equals minus 2 over 1. So x is minus 2.00. Correct. Example 3. A is 0, b is 0. If 0 is equal to 0 and 0 is equal to 0? True. Output. Infinitely many solutions. Correct. The key to solving algebraic problems like this is using logical and to capture the special case where both a and b are 0, and structuring the if-else chain to deal with the exceptions before the general case. Exercise 5. 1. The problem review. This is exercise 5. Write a program that takes 2 values, month and year, as input and outputs the corresponding number of days in that month. This is a multi-layered logic problem. We have a general rule for most months, and a special nested rule for February that depends on the year being a leap year. This is a great exercise for structuring complex if-else statements. 2. Required setup. Input. Since months and years are always whole numbers, we'll use the integer data type for both. 3. The core logic, the leap year check. We can't determine the days in February without first checking if the year is a leap year. This is a complex condition that uses logical and illogical, or a year is a leap year if it is divisible by 4 and not divisible by 100, or it is divisible by 400. We'll use a Boolean-like integer variable isLeap to store the result of this complex check. 4. The core logic, the month check. Since the month can be one of 12 distinct values, a switch case structure is the cleanest way to handle the logic. 5. Key takeaway. This problem demonstrates the power of combining structures. We used a complex set of logical operators to create a single Boolean variable, isLeap. We then used a switch case for efficient multi-way branching, and inside one of the cases, case 2, we used a simple if-else to resolve the final number of days. 1. Introduction. This is a logic problem in our series, reading a number from 1 to 999 in words. Our strategy is a 3-part breakdown using mathematical operators. Extract and process hundreds, n over 100. Extract the remainder, n mod 100. Use extensive if-else chains to handle tens, 20 to 99, teens, 10 to 19, and ones, 1 to 9. 2. Full C code implementation. Three. Step-by-step logic explanation. Step 1. The hundreds check. We start by isolating the hundreds digit using hundreds_digit equals n over 100. We then run a long if-else, if chain to print the word 100 through 900. Crucially, we then calculate the remainder, last_2_ equals n mod 100. If this remainder is not 0, meaning the number is not exactly 100, 200, etc., we print the connecting phrase and Step 2. The special case teens, 10 to 19. The numbers 10 through 19 are exceptions. 10, 11, 12, 13, etc. We use a separate if block to check specifically for this range. If last_2_ is greater than or equal to 10 and last_digits is less than or equal to 19. Inside this block, a dedicated chain of if-else if prints these unique words, preventing them from being broken down into tens and ones. Step 3. Tens, 20 to 99, and ones. If the number is not a teen, we proceed to handle all numbers from 20 up to 99, and finally the single digits, 1 to 9. We separate the tens and ones. Tens_digit equals last_2_ over 10 and ones_digit equals last_2_ digits mod 10. A long if-else if chain prints the tens word 20 through 90. If ones_digit is not 0, we print a hyphen and then use another if-else if chain to print the final ones word 1 through 9. Case 3, single digits 1 to 9. This case is for the case when you enter a one-digit number. This multi-step conditional breakdown ensures every number from 1 to 999 is converted correctly, without needing complex data structures. 1. The problem review. This is an excellent problem. Exercise 1. Input for arbitrary real numbers. Find the maximum value. Condition. The program can only use a maximum of 2 variables. The key to solving this is recognizing the analytic trick. We don't need 4 variables to store the inputs if we process them sequentially and only need to keep track of the current maximum. 2. The analytical trick and variable setup. We are limited to 2 variables. Here is how we will use them. Number. This variable will be reused to hold each of the 4 inputs one after another. A, B, C, D. Max_value. This variable will store the largest number found so far as we check the inputs sequentially. Since the inputs are real numbers, we must use the double data type, Lesson 2.02. 3. Step-by-step logic implementation. Step 1. Initialize the maximum, input A. We must read the first number A and use it to initialize our max underscore value. Step 2. Check input B. We reuse the number variable to read the second input, B. We then use a simple if statement, lesson 3.01, and a comparison operator, greater than, lesson 2.06, to check if the new number is greater than our current maximum. Step 3. Check input C. We repeat the exact same logic for the third number, C. The number variable is overwritten again. Step 4. Check input D and output. Finally, we repeat the logic for the fourth number, D. After this final check, the max underscore value must contain the absolute maximum of all four inputs. 4. Conclusion and key takeaway. This solution uses only the two required variables, number and max underscore value. The key to solving this kind of constraint problem is reusing variables and processing data iteratively. You don't need to store all the data simultaneously. You just need to keep track of the most important result found so far. This kind of logical thinking is what separates good coders from great coders. Exercise 2. 1. The problem review. This is the ultimate test of your Section 2 knowledge. Exercise 2. Input two positive integers a and b. Find the maximum value. Rule. Conditional statements, if, else, switch, are not allowed. 2. The analytical trick, using 1 and 0. The core concept is this. In C, a comparison operator, like is greater than or equal to, always returns either 1, true, or 0, false. We can exploit this property by using the result of a comparison as a multiplier. Any number multiplied by 1 is itself. Any number multiplied by 0 is 0. This means we can design an expression where the non-maximum number is guaranteed to be multiplied by 0 and the maximum number is guaranteed to be multiplied by 1. 3. Step-by-step logic implementation. We need 4 integer variables, a, b, and 2 temporary variables, max underscore a and max underscore b, to hold the result of the multiplication, plus the final max. For logic trace, let's trace how the program makes the choice without using any if statements. In every scenario, the logic works. The value we do not want is cancelled out by being multiplied by 0, and the correct maximum value remains multiplied by 1. 5. Conclusion and key takeaway. This incredible mathematical shortcut proves that in C, you can often replace complex control flow structures with creative use of operators. While in professional code, we almost always prefer the readability of the if-else statement. 1. The problem review and core difficulty. This problem asks us to find the number of days in a given month and year, but with a huge constraint. No conditional statements, if, else, switch are allowed. Normally, this requires 3 branches, 31 days, January, March, May, July, August, October, December, 30 days, April, June, September, November, 28, 29 days, February, leap year check required. Since we cannot use if, we must use arithmetic and the power of the logical operators and or and comparison operators, greater than equal to, lesson 2.06 and 2.07, which result in 1 true or 0 false, to build a formula. 2. The solution strategy. We will use a combination of 3 variables to represent the 3 possible results, 31, 30, or 28, 29, and multiply them by a Boolean expression that evaluates to 1 only when that result is the correct one. The final answer will be the sum of these 3 calculated parts, where only one of the parentheses yields a non-zero value. 3. Step-by-step logic implementation. We start by setting up the input for month and year. Step A. Calculating days in February, 28 or 29. We need the leap year logic, Lesson 2.10. Exercise 5. A year is a leap year if year mod 4 is equal to 0 and year mod 100 is not equal to 0, or year mod 400 is equal to 0. We can use this logic to directly calculate whether February has 29 days, result 1, or 28 days, result 0. Step B. The 31-day rule, odd, even trick. Most 31-day months, excluding August, are odd-numbered 1, 3, 5, 7, 9, 11, or August 8, and December 12. We use the modulus operator to check if the month is odd or even. Odd months, 1, 3, 5, 7 month mod 2 is not equal to 0 is true 1. Even months, 4, 6, 9, 11 month mod 2 is not equal to 0 is false 0. We combine this with the month number to get a clean Boolean result. Step C, the final formula. Now we combine all the logic into one final, non-conditional expression. 4. Complete code and key takeaway. This solution uses the power of C's Boolean evaluation, true equals 1, false equals 0, to selectively activate the correct number of days without relying on any if statements. Loop, Part 1 Basics. Exercise 1. 1. The problem review and the necessity of looping. We are starting our new section. Loops. The first problem is exercise 1. Input a positive integer n. Calculate the sum s, n, where s, n, equals 1 plus 2 plus 3 and continues up to n. A program needs a loop to efficiently repeat an action many times. This structure prevents us from writing code manually for every single number, especially if n is large. 2. Setup and key variables. We need 3 variables for any summation loop. N, the integer input, the final limit. Sum, the accumulator variable which starts at 0. We use long for safety. I, the iterator or counter variable which starts at 1. 3. The core logic, the while loop. We use the while loop, ensuring we include the 3 essential components. 4. Logic trace, example. N equals 5. Let's trace the loop for the input n equals 5. Start. Sum is 0, I is 1. I equals 1. 1 is less than or equal to 5, true. Sum becomes 1. I becomes 2. I equals 2. 2 is less than or equal to 5, true. Sum becomes 3. I becomes 3. I equals 3. 3 is less than or equal to 5, true. Sum becomes 6. I becomes 4. I equals 4. 4 is less than or equal to 5, true. Sum becomes 10. I becomes 5. I equals 5. 5 is less than or equal to 5, true. Sum becomes 15. I becomes 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 15. This simple loop structure efficiently solves the problem for any value of n. Exercise 2. 1. The problem review and the core change. Our next problem is exercise 2. Input a positive integer n. Calculate the product s, n, where s, n, is equal to 1 multiplied by 2 multiplied by 3 and continuing up to n. This product is also known as the factorial of n, written as n. The structure of the solution is almost identical to the previous summation problem, but with 2 critical changes. Operation. We switch from the addition operator to the multiplication operator. Initialization. The accumulator variable must start at 1, not 0. 2. Setup and the key variable change. If we initialize the product variable to 0, the multiplication inside the loop will always result in 0, because anything multiplied by 0 is 0. Therefore, the accumulator must start at 1. We will use the variable name product instead of sum for clarity. 3. The core logic, the while loop. The structure is the same. Initialize I to 1, loop while I is less than or equal to n, and update I by incrementing it by 1. The only change is the operation within the loop body. 4. Logic trace, example, n equals 5. Let's trace the loop for the input n equals 5. Start. Product is 1, I is 1. I equals 1. 1 is less than or equal to 5, true. Product becomes 1 times 1 equals 1. I becomes 2. I equals 2. 2 is less than or equal to 5, true. Product becomes 1 times 2 equals 2. I becomes 3. I equals 3. 3 is less than or equal to 5, true. Product becomes 2 times 3 equals 6. I becomes 4. I equals 4. 4 is less than or equal to 5, true. Product becomes 6 times 4 equals 24. I becomes 5. I equals 5. 5 is less than or equal to 5, true. Product becomes 24 times 5 equals 120. I becomes 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 120. Exercise 3. 1. The problem review and the operation. Our next challenge is exercise 3. Input a positive integer n. Calculate the sum s, n, equals 1 squared plus 2 squared plus 3 squared, continuing up to n squared. This problem is a combination of the first two. It's a summation, so our accumulator, sum, must start at 0. The repeated operation inside the loop is now calculating the square of the current number, I times I, before adding it to the total. 2. Setup and variable initialization. The setup is identical to our first summation problem. We need n for the limit, sum for the result, and I for the counter. 3. The core logic, the while loop and squaring. The loop structure remains the same, but the calculation inside the body is where we implement the squaring. In C, we calculate a square by simply multiplying a number by itself, I times I. 4. Logic trace, example, n equals 3. Let's trace the loop for the input n equals 3. Start. Sum is 0, I is 1. I equals 1. 1 is less than or equal to 3, true. Sum plus equal 1 times 1 equals 1. I becomes 2. I equals 2. 2 is less than or equal to 3, true. Sum plus equa, 2 times 2 equals 4. Sum is now 1 plus 4 equals 5. I becomes 3. I equals 3. 3 is less than or equal to 3, true. Sum plus equal, 3 times 3 equals 9. Sum is now 5 plus 9 equals 14. I becomes 4. End. The condition 4 is less than or equal to 3 is false. The loop terminates. The final output is 14. Exercise 4. 1. The problem review and the modulo trick. Our goal in exercise 4 is to input a positive integer n and output all even values in the range from 1 to n. This problem requires two structures working together. The loop, to check every number from 1 up to n. The conditional check. Inside the loop, we use an if statement and the modulo operator to check if the current number is even. Remember, a number is even if dividing it by 2 leaves a remainder of 0. 2. Setup and initialization. We need integer variables n for the limit and I for the counter, starting at 1. 3. The core logic, loop, and condition. We use the while loop for repetition and the if statement as a filter. 4. Logic trace, example, n equals 5. Let's trace the loop for the input n equals 5. Start. I is 1. I equals 1. 1 is less than or equal to 5, true. 1 mod 2 is equal to 0, false. Nothing prints. I becomes 2. I equals 2. 2 is less than or equal to 5, true. 2 mod 2 is equal to 0, true. Print 2. I becomes 3. I equals 3. 3 is less than or equal to 5, true. 3 mod 2 is equal to 0, false. Nothing prints. I becomes 4. I equals 4. 4 is less than or equal to 5, true. For mod 2 is equal to 0, true. Print 4. I becomes 5. I equals 5. 5 is less than or equal to 5, true. 5 mod 2 is equal to 0, false. Nothing prints. I become 6. End. The condition 6 is less than or equal to 5 is false. The loop terminates. The final output is 2, 4. Exercise 5. 1. The problem review and the divisor rule. Our goal in exercise 5 is to input a positive integer n and list all of its divisors. What is a divisor? In mathematics, a number I is a divisor of n if n can be divided by I with a remainder of 0. This immediately tells us we must use the modulo operator. The loop structure will be loop. Check every number I starting from 1 up to n. Condition. Use if n mod I is equal to 0 to check for a 0 remainder. Action. If the remainder is 0, the number I is a divisor, so we print it. 2. Setup and initialization. We need integer variables n for the input number and I for the counter, which will serve as our test divisor. 3. The core logic, loop, and modulo check. We use the while loop to ensure we test every single number from 1 up to n. 4. Logic trace example. N equals 6. Let's trace the loop for the input n equals 6. Start. I is 1. I equals 1. 6 mod 1 is equal to 0, true. Print 1. I becomes 2. I equals 2. 6 mod 2 is equal to 0, true. Print 2. I becomes 3. I equals 3. 6 mod 3 is equal to 0, true. Print 3. I becomes 4. I equals 4. 6 mod 4 is equal to 0, false. Remainder is 2. I becomes 5. I equals 5. 6 mod 5 is equal to 0, false. Remainder is 1. I becomes 6. I equals 6. 6 mod 6 is equal to 0, true. Print 6. I becomes 7. End. The condition 7 is less than or equal to 6 is false. The loop terminates. The final output is 1, 2, 3, 6. Exercise 6. 1. The problem review and logic synthesis. Our final basic loop challenge is exercise 6. Input a positive integer n and calculate the sum of its divisors. This is essentially the combination of two previous exercises. Finding divisors, exercise 5, we use the if n mod I is equal to 0 check inside the loop. Summation, exercise 1, we use an accumulator variable, sum, initialize to 0 and add to it inside the conditional block. 2. Setup and initialization. We need 3 variables. N for the input, I for the counter, test divisor, and sum to hold the running total. 3. The core logic, loop, condition, and accumulation. We iterate through all numbers from 1 to n. The if statement determines if the current number I is a divisor, and if it is, the summation happens immediately inside that block. 4. Logic trace example. N equals 6. Let's trace the loop for the input n equals 6. The final output is 12. Part 2, Advanced. Exercise 1. 1. The problem review and the decomposition trick. Our challenge in exercise 1 is to input a positive integer n and output all of its digits in reverse order. For example, 123 becomes 3, 2, 1. The hint is the key. We must repeatedly use the modulo operator, mod 10, and integer division, over 10. This two-step process allows us to peel off the digits one by one. 2. Setup and the loop condition. We need 2 variables. N for the input number, which we will modify, and digit to store the result of the modulo operation. The loop must continue as long as n is greater than 0. Once n becomes 0, after all digits have been peeled off, the process stops. 3. The core logic, loop, modulo, and division. Inside the while loop, we execute the 2 crucial steps for every digit. 4. Logic trace example. N equals 123. Let's trace the loop for the input n equals 123. The final output is 3, 2, 1. This method perfectly separates the digits of any positive integer n, and it's the most common way to analyze the components of a number in programming. The next exercise, Advanced Exercise 2, is a variation of this. We'll use this same structure but add a condition to filter out only the even digits. Are you ready? Exercise 2. 1. The problem review and logic filter. Our challenge in Exercise 2 is to input a positive integer n and output only the even digits found within it. We reuse the core digit decomposition loop we just learned. Extraction. Get the last digit using the modulo operator, mod 10. Modification. Remove the last digit using integer division over 10. The new requirement is the filter. After extracting a digit, we must check if that digit is even. We do this using the modulo operator again. If digit mod 2 is equal to 0, 2. Setup and initialization. We need integer variables n for the number and digit to hold the extracted value. 3. The core logic loop, extraction and filtering. The if statement is nested inside the while loop, allowing us to filter every digit as we extract it. 4. Logic trace, example. N equals 1234. Let's trace the loop for the input n equals 1234. The final output is 42. By combining the digit extraction loop with a conditional filter, you gain powerful control over number analysis. Exercise 3. 1. The problem and the floating point trap warning. Our task is to calculate the sum s, n, equal to 1 plus 1 divided by 2 plus 1 divided by 3, continuing up to 1 divided by n. The most important concept here is the floating point trap. If we use integer types for the division, e.g., 1 divided by I, C will perform integer division, and any result less than 1, like 1 divided by 2, will be truncated to 0. To get the correct decimal answer, we must declare the sum variable as a double for real numbers. Force the division to be a floating point operation by writing double 1 over I. 2. Full C code implementation. We will use a while loop to iterate from I equals 1 up to n. 3. Step-by-step logic explanation. Initialization. We use double sum equals 0.0 to correctly accumulate the decimal fractions. The counter I starts at 1. The division. The line of code sum equals sum plus double 1 divided by I is the core of the solution. The typecasting double forces the division to use floating point rules, ensuring accurate results, e.g., 0.5 instead of 0 for 1 divided by 2. The output. We use the format specifier %.6lf to display the result as a double, formatted to 6 decimal places, matching the example output. Exercise 4. 1. The problem review and the series formula. Our final advanced challenge is Exercise 4. Input a positive integer n and calculate the sum s, n, equals 1 plus 1 over 3 plus 1 over 5, continuing up to 1 over 2 times n plus 1. The main logic requires 2 key components. Data type. The sum must be a double to handle the fractions. Loop logic. We generate the odd denominators using the formula 2 times I plus 1, where our counter I starts at 0 and goes up to the input n. 2. Setup and variable initialization. We need 3 variables. N for the limit, sum for the result, and I for the counter. 3. The core logic, loop, and formula. The loop continues as long as I is less than or equal to n. We calculate the odd denominator using the formula 2 times I plus 1 inside the loop. 4. Logic trace, example. N equals 2. Let's trace the loop execution for the input n equals 2. For the input n equals 2, the final result is 1.533333. Exercise 1. 1. The problem review and the simulation approach. The sock problem asks, given n pairs of socks and a new pair arriving every m days, how many days until the stock runs out? We cannot solve this directly with a simple arithmetic formula because the stock change is dynamic. Every day we lose one pair, but periodically we gain one pair. The correct way to solve this is to simulate the process using a while loop that iterates through the days. The loop will continue as long as the stock n is greater than 0. 2. Setup and key variables. We need 3 integer variables. N, the current number of stock pairs, the stock. M, the period after which a new pair arrives. Days, the counter for the total time elapsed, initialized to 0. 3. The core logic, the simulation loop. Inside the loop, we simulate the events of a single day. 4. Logic trace example. N equals 2, M equals 2. Let's trace the loop for the input N equals 2, M equals 2. The loop stops on day 3 when the stock finally hits 0. The output is 3. Exercise 2. 1. The strategy, the left-to-right loop. The correct way to solve this with a loop is to process the number from left to right. We will use a long variable called scale_divisor, which will represent 1 billion, then 1 million, then 1,000. A while loop will divide the scale_divisor by 1,000 in each iteration, moving us from the billions block to the millions block, and so on. 2. Full C code implementation. Three. Logic explanation. Trace the loop for n equals 2,147,483,647. Find scale. The code first finds the starting scale_divisor. For 2.1 billion, the starter is 1 billion. Main loop, iteration 1, billions. Scale_divisor is 1 billion. Current underscore block equals n over 1 billion. Result is 2. The 3-digit logic runs on 2. It prints 2. The scale logic runs. It prints billion. N becomes the remainder, 147,483,647. Scale_divisor becomes 1 million. Main loop, iteration 2 millions. Scale_divisor is 1 million. Current underscore block equals n over 1 million. Result is 147. The 3-digit logic runs on 147. It prints 147. The scale logic runs. It prints million. N becomes the remainder, 483,647. Scale_divisor becomes 1,000. Main loop, iterations 3 and 4. The loop repeats this exact process for thousands, 483, and the last block, 647.